Welcome to the Belimo Knowledge Seminar. Today marks the beginning of a knowledge series on the topic of hydronics and valve selection in building technology. In the first part of this series, we will look more closely at the most common types of basic hydronic circuit arrangement, and the various types of manifold. The seminar refers to basic physical principles, and as such, it is manufacturer independent and generally applicable. I have the privilege of guiding you through the seminar today. Why water as an energy carrier, rather than air? Water has a specific thermal capacity that is more than 4 times larger, and a density that is more than 900 times that of air. If you were to attempt to transfer the same quantity of energy with air as with water, you would require more than 3,700 times the volume of air. The pipe cross-sections required with water as the energy-carrying medium are significantly smaller than with air, as the energy-carrying medium. With correct planning and design, a very high level of thermal comfort can be achieved with water as an energy-carrying medium. Why are there different hydronic circuits? And when should each be used? Is there not one that is suitable for every application? I would like us to consider a comparison. There are many different types of shoe. You choose the suitable shoe, depending on your requirements. Imagine, you were playing a tennis match. Which type of shoe would you choose? Wellington boots. Possible, but not logical. Here's another example. You want to climb the north face of the Eiger. Would you choose flip-flops as your footwear? With hydronic circuits it is very similar. There are different requirements, for example, pressurized or pressureless manifolds. Consumers that are operated with varying inlet temperature, depending on the exterior temperature, for example static heating circuits. Or heat generators, for example condensing boilers, which should be operated with a cold return flow, on account of their high energy efficiency. By now it should be clear. You could always use the same hydronic circuit. But for many applications this would be an absolutely terrible idea. What is hydronics? The theory of hydronics describes the flow behavior of liquids. Using hydronics, signals, forces, and energy can be transferred. In heating and cooling systems, heat transport is guaranteed using water or water-glycol mixtures within enclosed circulation systems. For example, the heating water flows from the boiler to the radiator via heating pipes. Here the heating water releases its energy into the radiator and into the room. The cooled heating water flows back to the heat generator, where it is heated again. The circuit starts over again from scratch. In order to ensure the desired room climate, buildings must be heated and/or cooled. The task of a heating or cooling system involves providing, distributing, and releasing the necessary energy as required. The required energy is directed to the consumer via the medium of water, or via water-glycol mixtures. Multiple consumers are generally grouped together on one manifold, and are supplied via one or more heat generators or chillers. The manifold is the component between the generator and the consumers. The task of the manifold is to make the energy available to the consumers as required, and with the required flow temperature. The selection of the suitable system will depend on the requirements and the selected components on the generator and consumer sides. In building technology, there are essentially 2 types of manifold: differential pressureless manifolds, also known as low-pressure manifolds, and differential pressure manifolds, also known as pressurized manifolds. Due to their construction, differential pressureless manifolds achieve almost the same pressure in the flow manifold and in the return collector. Low-pressure manifolds. Previously, a generator pumped the water to the flow manifold under pressure. If it was not removed from here, it would flow to the return collector via a direct link, and from there would be returned to the generator, unused. This had numerous disadvantages. As a result of the constant overflow of the supply water into the return collector, the return temperature increases. This significantly limits the utilization of calorific value in relation to the supply temperature, and is not permitted in the case of district heating. Because a proportion of the supply water always flows back to the generator unused, this results in an increased energy requirement for the pump. Differential pressureless manifolds. Nowadays, the individual heating circuit pumps, in conjunction with the control valve, collect the water directly from the generator, or are hydronically decoupled from the buffer storage or the hydronic separator. As such, only the supply water that is actually required is collected. Generally speaking, this variant is also suitable for the utilization of calorific value and for district heating. Continuous return temperature control, as with the variants used historically, does not take place. On account of their construction, differential pressure manifolds have a higher pressure in the flow manifold than in the return collector. With pressurized manifolds, a pump pumps the water to the flow manifold under pressure. From here, the water must flow to the consumers via the heating circuit, before returning to the return collector and generator. Due to the higher pressure losses on the water side, differential pressure manifolds are increasingly used on the generator side. The current output to heating or cooling consumers can be influenced by two factors. Volume flow control or temperature control. The choice between a volumetric flow or temperature-controlled system will be based on the consumer's requirements. Regulate volumetric flow, referred to as volume-controlled or throttle-controlled. Regulate temperature, referred to as temperature-controlled or mixing-controlled. In the case of volume-controlled circuits, the volumetric flow is influenced by the control valve. This produces the change of output at the consumer. The quantity of water passing through the consumer is variable. The supply temperature for the consumer is always the same. With the throttling circuit, a position change at the control valve results in a change in the flow rate in the consumer and generator circuit. The current output at the consumer is adjusted by means of a change in the volumetric flow rate. The supply temperature always remains constant. Properties of the throttling circuit. The flow rate at the consumer and at the generator is variable. The manifold must have a pressurized design. Typical applications of the throttling circuit are control valves for radiators, zone valves for individual room control, control of small, zonal post-heating coils, control of water or water heat exchangers, or control of air coolers with controlled or maximum dehumidification. Water heating. Advantages of the throttling circuit are a high temperature differential between the supply and return flow is possible. This is ideal for calorific value utilization and for heating by means of district heating. The throttling circuit is simple to control. Disadvantages of the throttling circuit are strong hydronic influence on the entire system when changing the position of just one control valve. However, through the use of pressure-independent control valves, there is no longer any hydronic influence on the different consumers. High temperature stratification in consumers during operation at partial load. Cooling of the pipelines during downtime. Proportionally controlled pumps are required to avoid overheating when the valves are closed, whereby speed-controlled pumps should now be the standard. Not suitable for air heating coils, which are exposed to external air or frosty air. Here there is a risk that the heating coil will freeze, a risk of frost. With a diverting circuit, a position change at the control valve has an influence on the water quantity that flows through the consumer and the bypass. The water quantity via the bypass flows directly into the return flow, without being directed via the consumer. The current output at the consumer is controlled by means of a change in the volumetric flow rate, with a constant supply temperature. Properties of the diverting circuit. The flow rate at the consumer is variable. The flow rate at the generator is constant. The manifold must have a pressurized design. Typical applications of the diverting circuit are fan coil, also referred to as convection heater, air cooler with controlled dehumidification, and air reheater, if temperature stratification is permitted at partial load. Advantages of the diverting circuit are no influence on the flow rate or the pressure in the generator circuit. Quick startup if the valve is positioned close to the consumer. Low hydronic influence on the individual circuits due to the constant flow rate in the generator circuit. Disadvantages of the diverting circuit are at partial load, the flow water flows back directly to the generator, via the bypass. The high return temperatures in the partial load range limit calorific value utilization significantly, depending on the supply temperature. This is not permitted in the case of district heating. Standing losses as a result of continuous generator circuit circulation have a negative impact on energy efficiency. With temperature-controlled circuits, the mixing ratio of supply and return water is adjusted using the control valve. This produces a new supply temperature for the consumer. The supply temperature is generally controlled based on the outdoor temperature. The flow rate via the consumer remains constant. With the mixing circuit, a change at the control valve influences the quantity of return water that is mixed with the supply water via the bypass. The current output at the consumer is controlled by means of a temperature change with a constant volume of water. Properties of the mixing circuit. The flow rate at the consumer is constant. The flow rate at the generator is variable. The manifold should feature a pressureless design, so that the influence of supply pressures on the total characteristic curve at port AB is kept to a minimum. The goal is to guarantee that the volumetric flow rate via port AB is as constant as possible. Typical applications of the mixing circuit are weather-compensated flow temperature controls, air preheaters, air reheaters only a very small spread during partial load operation, or air coolers with dehumidification. Additional information. With pressurized manifolds, the use of an injection-type system with a two-way valve must be checked. Note regarding the ports of a control valve. Combined port AB is always shown as a blank triangle. Port A and port B are always filled in black triangles. Advantages of the mixing circuit are very high valve authority at pressureless manifolds. Good controllability on account of constant volumetric flow rate on the consumer side. Very low risk of freezing with air heaters. Very low temperature stratification in the consumer during partial load operation. Significantly reduced heat losses in the distribution network during partial load operation in comparison to the diverting circuit, and the injection circuit with a three-way valve. Disadvantages of the mixing circuit are the temperature level of the generator and the consumer should be roughly the same so that, in the design case, the valve can be opened 100% if possible. For consumers whereby the supply temperature is much lower than the generator temperature, for example in an underfloor heating system, a mixing circuit with fixed pre-mixing should be selected. The mixing circuit can practically only be used in hydronically decoupled systems. The mixing circuit with fixed pre-mixing is often also referred to as a double mixing circuit or a mixing circuit with constant bypass. By means of fixed pre-mixing with the balancing valve, also known as a fixed bypass, a specific proportion of the cooled return water is always mixed with the supply. Using the control valve, the quantity of return water that is mixed with the supply water can be adjusted. As a result, the maximum supply temperature at the consumer is always lower than the supply temperature at the generator. The current output at the consumer is controlled by means of a temperature change with a constant water quantity. The main advantage over the standard mixing circuit is that the three-way control valve works between 0 and 100%, as, at full load, the required return water flows via the fixed premix and not via port B of the three-way control valve. Properties of the mixing circuit with fixed premixing. The flow rate at the consumer is constant. The flow rate at the generator is variable. The manifold should have a pressureless design. Comment. With a pressurized manifold, the use of an injection circuit with a two-way valve must be checked. Typical applications of the mixing circuit with fixed premixing. All types of surface heating, such as underfloor heating, wall heating, ceiling heating, concrete core temperature control, or industrial surface heating. Advantages of a mixing circuit with fixed premixing are ideally suited for applications whereby the supply temperature of the consumer is much lower than the supply temperature of the heat generator. Very low temperature stratification at the consumer due to the high constant flow rate. Good controllability, as the control valve can be used between 0 and 100% across its entire working range, since, in the design case or at full load, the required return water flows via the fixed bypass, and not via port B of the control valve. Significantly reduced heat losses during full and partial load operation due to lower flow temperatures, in comparison to the diverting circuit and the injection circuit with three-way valve. Disadvantages of a mixing circuit with fixed premixing are: as a result of the fact that the generator's waterside pressure losses are much increased in comparison to previous types, the mixing circuit can practically only be used with systems with a hydronic separator or buffer storage. Using the control valve of the injection circuit with two-way valve, the quantity of return water that is mixed with the supply water via the bypass can be adjusted. Depending on the design and configuration of the consumer pump, the supply temperature of the consumer may be the same as the supply temperature of the generator, or even much lower. The current output at the consumer is controlled by means of a temperature change with a constant water quantity. Properties of an injection circuit with two-way valve. The flow rate at the consumer is constant. The flow rate at the generator is variable. The manifold must have a pressurized design. Typical applications of the injection circuit with two-way valve are weather-compensated supply temperature controls, air preheaters, air reheaters, here only very minor temperature stratification at partial load, air coolers with dehumidification, underfloor heating, wall heating, ceiling heating, concrete core temperature control and industrial surface heating. Advantages of the injection circuit with two-way valve are very low risk of freezing with air heaters, only minimal temperature stratification at the consumer, good controllability on account of constant volumetric flow rate on the consumer side, minor heat losses due to low supply temperatures at partial load, in comparison to the diverting circuit and injection circuit with three-way valve. Ideally suited for systems with low return temperatures, such as district heating or condensing boiler technology. The disadvantage of the injection circuit with two-way valve is strong hydronic influence on the entire system when changing the position of just one control valve. However, through the use of pressure-independent control valves, there is no longer any hydronic influence on the different consumers. With the injection circuit with three-way valve, the flow rate on the generator and consumer sides is always constant. Using the three-way valve, the injected supply water quantity at the generator is controlled. Because the consumer circuit pump, also known as the secondary pump, draws in a constant volumetric flow within the consumer circuit, the quantity passing through the second bypass varies, depending on the quantity of supply water at the generator. The current output at the consumer is controlled by means of a temperature change with a constant water quantity. Properties of an injection circuit with three-way valve. The flow rate at the consumer and generator is constant. The manifold must have a pressurized design. Typical applications of the injection circuit with three-way valve are air preheaters. Air reheaters, here only very minor temperature stratification at partial load. Air coolers with dehumidification. Advantages of the injection circuit with three-way valve are very low risk of freezing with heating coils. Only minimal temperature stratification at the consumer. Low downtime if the control valve is close to the consumer. Good control quality on account of the pending medium temperature, quick response, in particular with significant load change. Disadvantages of the injection circuit with three-way valve are at partial load, the water flows directly back to the generator via the bypass, just as with a diverting circuit. The high return temperatures in the partial load range limit calorific value utilization significantly, depending on the supply temperature. This is not permitted in the case of district heating. Standing losses as a result of continuous generator circuit circulation have a negative impact on energy. We would be happy to send you the information from this presentation as a handout in compact form. Use the QR code to download the document in PDF format. The document includes the most common basic hydronic circuits with the required selection criteria and standard applications, along with general dimensioning and design instructions, summarized on one denne A4 sheet. Thank you very much for your attention.